Okay, should I start?
Yes, Vincent, you have the floor.
Okay, so thanks a lot, Marcel. So this talk will be dedicated also to, of course, Anderson localization with ultra-cold atoms for more on the 3D part that I will discuss what we want to look there. Since I have also more time, I was, of course, asked by the organizer to do something a bit more general, and then I will take this opportunity somehow to present the general line of research of this Anderson localization with ultra-cold atom from first experiment to really recent development. And in some sense, there is some redundancy with what I've shown Martin, but here I will be somehow not entering too much to the detail, but try to focus more about the methods, what can we learn, and what are somehow the observable that we can get with our system. So another important thing to say is that I try to make quite general, but it's not exhaustive. It's not possible to do so. So I apologize if I'm not showing all the results that has been obtained in this domain. So, and as you will see, in fact, I will focus more on the experiment that has been done here in Palaiseau, since we have done quite a lot in the subject, so in the quantum gases group at Institut Optique. So just before starting, I just want to, of course, acknowledge all the people that has been working on this. So many PhD students since the early time of the 1D Anderson localization with Juliette, Billy here. And so of course, I skipped that. I just want to say that I have a few PhD students there and a postdoc that are listening now, which is Baptiste Lecout, which will be finishing his PhD, will defend on end of November. Yukun Liu and Zhudong is now a PhD student, and Azer is a postdoc on the team. So that's for the experimental team. Of course, I should say, mention, of course, Alain, which is leading the team with me, that you can see here and here. And so we can see both of them. So that's for the current version of us now on the screen. Okay, of course, I should also acknowledge the collaborators that we had on theory. And early time, we had Laurent Sanchez-Palencia that have done a lot of work on this subject. And I should also really acknowledge all the work that has been done with Dominique Deland, which cannot be there today, but I'm really, really grateful to him, to all what I could learn with this collaboration and interaction with him. So, and you have seen yesterday that he knows quite a lot about this Anderson localization. And of course, now we have this very nice collaboration within the Simons Foundation with Marcel and Shlitana on this is ongoing work. And really sorry for this bad quality image that I took from the website.
It's okay.
So let me start with a very rough slide showing the panorama of ultra-cold atoms and disorder. Just to say that the typical system is we take a BC, we let them propagate in a disorder system, and we look at Anderson localization. So as you maybe know, the first realization of it was clearly done in 1D more than 10 years ago now in the group and also in Florence. And the domain has, of course, evolved. And you have an example of what has been done very recently in 2D. And if you see that there was, let's say, more than 10 years to achieve that, it gives you an idea of the difficulty of the domain to have clear signature of localization properties. So talking about Anderson localization, so if you remember the talk of Dominique yesterday and also the one of Sergei Skipetrov, clearly I think we can clearly say that the challenge, or at least one of the most important one, is to tackle the 3D Anderson transition. This appears when you are in 3D and you increase the disorder sum from somehow weak disorder when you have diffusion. It can be eventually renormalized by these weak localization processes, but the system remains diffusive in weak disorder. But then if you increase very large to reach very strong disorder, which is pinpointed by this so-called Joffre-Regel criterion, when somehow the double wavelengths or the wavelengths of the wave that you consider is on the order on the MIFRE path, transport path, sorry. Then when it is close to 1, which means that the wave barely oscillates between two scattering events, then you expect to reach the transition toward the localization, which is, I insist, which you have to think of it like extreme disorder. So in this picture is not the one that I will consider during the talk, but Nick Levant an equivalent one somehow, where now I fix the disorder amplitude and the transition manifests in an energy threshold, which we call the mobility edge. And at high energy level, you have diffusion, and low-lying energy states are supposed to be localized. And really the goal is to try to study this mobility edge and look at the critical regime around that. So as was also said, so all this Anderson localization story is for single particle. But now if you add interaction in your system, you can have even a more interesting configuration. At least the system is even richer, and you can either look to the equilibrium state, which is referred to the Bose-Glass phase. There was a lot of work doing within the field of ultra-cold atom to try to look at that. And since now few years, a new paradigm somehow of localization is called the many-body localization, which is related to thermalization. And you will hear a lot tomorrow on that. And a bit also, I believe, on the talk of Nicolas. So as I said, for this talk, I will concentrate on this 3D Anderson transition. And as I will show, in fact, there has been already evidences of this transition on experiment. At least 3 experiments has been done on this. One by Brian DeMarco in US in 2011. In fact, roughly at the same time in Palaiso in our group, and a more recent one in Florence. But as you will see, so it's already clear, I think, for all of them that it's a difficult experiment, but you will see that for the moment, there is a real bottleneck for trying to really look precisely at this Anderson transition. And in fact, there has been recently some numerical work done by the Dominique Deland and co-worker, and Giuliano, which maybe is here today, I don't know. And what they have shown is looking at numerics that indeed there was quite strong discrepancies between the results, the experimental result that has been shown so far and the numerics. So it's clearly called for further investigation of this Anderson transition. So that's motivate what I will present in the following, of course. I just want to say that, of course, there is another approach using cold atoms if you want to study localization, which is looking what we call dynamical localization in Kirk-Water systems. So I will not consider this story there within this talk, but you will have a talk from Jean-Claude Garot later in the afternoon that will tell you many things about this very nice system to probe localization.
Tomorrow, actually.
It's tomorrow. Okay, then it's tomorrow. Okay. Well, so I will not consider this Kirk-Water system, which are also very nice system to study localization. But there is a mapping somehow between what we call spatial localization, the genuine Anderson localization, and this dynamical localization. So here it's the outline of the talk. So the first part will be rather long, and I tried here as promised to give you rapid overview of the approach of the ultra-cold atom in disorder, what has been done, what is the disorder we use. And I also will take some time to highlight something which is not so well known on this system, is that all the richness that you can get looking in momentum space, what I call momentum space signatures, and that will be an introduction part somehow to the talk of Nicolas that will just follow. Then the second part will be dedicated to the study on the Anderson transition, try to explain what is the problem, the bottleneck somehow. And I will also explain the importance of what is called the spectral function, which is a venerable concept in condensed matter physics, or in physics in general, in this context. And I know that maybe I will be rather long, so maybe I will be stopped somewhere. I try to be at least around there, but clearly what I want to say is that there is a poster from Pierre Pelletier, which is working now on the spectral function. And if you want more detail on this, then I strongly suggest that you look in this. The last part, and as I said, this really depends on the time. So Marcel, you have to stop me at one point. Then I will describe the more recent advance where we have developed a new scheme to try to tackle this Anderson transition and to be able to measure this spectral function, and I will explain why this is important. Okay, and of course I will conclude and give maybe some prospects. Okay, so I should of course start somehow this first general part by this standard advertising slide about the ultra-cold atoms. just to say that they're, of course, very well controlled and tunable system. You can play with geometries, imaging, interaction. You can even try to simulate artificial magnetic field if you want. And this allows you to simulate a lot of systems which are strongly connected to condensed matter physics, which I'm not discussing in too much, but for instance, here you recognize the transport properties here, and also the conduction experiment, which is very similar to the one shown by Martin, but the first experiment of this was done in a group of Tillman and Stimber by Jean-Philippe Pointu. So here we will, of course, be interested by disorder systems. So we have a lot of tools to create disorder. So I believe you will see one which is called quasi-crystal or bichromatic lattices. So I won't comment too much this one. That can be done in 1D or 2D. The one that I will comment today is the so-called laser speckle disorder potential. And the reason why is that it's very easy to produce and it has been very widely used in the community, and especially to study the Anderson transition in 3D. And as also what you have learned in the previous talk, that now using SLM, spatial light modulator, in fact, if you are in the 2D configuration, you can, of course, create arbitrary potentials, so a clean one or a disorder one, depending on what you want to do. So let me now focus on this laser speckle disorder because it is the one that's been used for 3D Anderson localization. So in fact, it's really easy to create this. You just have to shine a laser. You put here a focal length just to focus on one point, and you put a wave plate. And if you look here on the focal point, you don't have a nice spot, but you have something which is really messy, which look like that. So you have grain of light, which are bright, surrounded by dark areas. And the good things of this speckle is that it's very easy to produce. You have somehow disorder for free. And the other very important things is that its statistical properties are very well known and very, very robust. So we can really trust them on experiment. So for instance, a first property of interest, where also I won't comment it too much today, is that we can show that the intensity distribution of this speckle pattern is an exponential one. And here it is translated somehow in potential and not in intensity, because the idea is that we can translate this intensity pattern directly as a potential on the atom just by shining light, which is rather far detuned from an atomic resonance. And depending on the detuning, which we call blue detuning and red detuning, is the energy is lower than the transition, then the potential is simply scaling directly proportional to the intensity and divided by the detuning. So we can call, if delta, the detuning is positive, we call it the blue detune or repulsive potential, because then we create barriers, random barriers somehow for the atoms. And we can also play in an inverse case where now the bright spot here transfer to wells, and that's which is the red detune case we call the attractive case. So just to say that in fact these two potential, here I won't comment too much, but in fact they are very different in essence since they have different probability distributions, so that they have different statistics. So that's for the potential that we can do. And if I come back to the statistical properties of this speckle. So I already talked about this exponential intensity distribution, which I will not consider too much today. But another important one that has been also discussed a bit by Martin and of course by Dominique yesterday is the speckle grain. If you create a potential with light, of course, it has a certain size, and the minimal size that you can do is given by the diffraction limit. And in fact, it's easy to show that for the speckle pattern, the typical size here of the speckle grain is indeed given by the diffraction limit. And this size is very important for the physics because it defines an energy range or a temperature range or a temperature range for the experiment. So if I recall the naive argument said by Dominique yesterday, which is in fact working nicely, which is to state if you want to expect some quantum effect when you propagate atoms in this landscape, okay, at least disorder, not the landscape of Marcel, sorry, but just in the disorder potential, then I think it's fair to expect that you will have quantum effects if the de Broglie wavelength of the atoms is larger, at least, than the correlation, the speckle grain size. So if you translate this length scale can transfer in an energy scale where we define the correlation energy, which is nothing else than the price to pay if you want to confine the particle on the size of the speckled grain. And the energy should be the kinetic energy and of course temperature of atom. If you want to have quantum effect, should be much larger, at least much smaller, at least smaller than this correlation energy. And in fact, if you translate these kind of things for the typical size that you can create with light, which is, let's say, half a micrometer, just to give you a typical number that we reach in experiment, then this energy can be written in temperature is given at 10 nanokelvin. So here, again, you understand why Martin insists a lot about the need of ultra-cold atoms and starting with BEC in his talk. So you have to realize for people which are not working on Bose-Einstein condensate that this temperature is already 1 order of magnitude lower than typical temperature for the transition of Bose-Einstein condensate. So it corresponds to already very low energy scale, even for the domain of condensate, of cold atoms. And that's why in the following, I will somehow, I call our domain the ultra cold atoms system. So, okay, let me just briefly present the scheme of 1D before going to 3D, sorry. So once we have the disorder potential, the typical ID, the natural scheme somehow of the domain is we take a BEC, for instance. This we know how to produce it nicely, and then we release a trap and we let it expand. And then if we put nothing, then we expect ballistic. If we put disorder, then maybe there is a part ballistic, maybe there is some diffusion, as discussed by Dominique yesterday. And of course, what we want to see is localization. That means after some time, it expands and then it stops after some time. So this general scheme, it's really the one that is shown here. We take the BEC here at the beginning. This gray area corresponds to some magnetic field at the beginning. And here there is a tube, which is nothing else but a beam, which is red deuterium to allow the atoms to guide the atom along 1D direction. Then we release it. And then after some time, we find something which which is in fact stable, which then you have to believe me here. It doesn't move. And if we look on the wings, we find this very nice exponential decay over more than 1 decade. And that we could, more importantly, it is very key feature in the experiment, that we could compare directly with theoretical prediction that without any somehow adjustable parameter. So you can do ab initio prediction of this. We do the experiment and it was working very nicely. So the experiment was done in 2008. And as I said, Laurent Sanchez-Panucia was the theory that really tells us in which experimental domain we should go. So that's very nice experiment. I'm not commenting the one which was done similarly at the time in Florence, which is in bichromatic lattices. So it's not exactly Anderson localization, but there is localization there. It's called the Aubry-André model. And I believe Ulrich Schneider will talk a bit about it. So this is very nice, but somehow, if you think of all the promises of the domain, which the ultra-cold atom will tell you, well, we control all the microscopic, we control the matter waves. And the idea, if you think once again of what was said by Dominique, is that there is different scales, time scale, but length scale in the problematics of Anderson localization. You have the first scale, which is the mean free path. Then you expect some diffusion and maybe renormalization by loops, so which is called the weak localization, which is somehow the mechanism at the heart of localization. And then if you wait for a very long time, you have the localization. So here I show you just the end of the process where we find something which is indeed localized and that we can compare with theory, but in between it will be good if we want to tackle even more complex system to be able to observe the mechanism at the heart of localization. So as I said, this maybe if we want to really compare in more complex system, can we have also direct measurement of the mean free path, or the same things that the mean scattering time? So it's just the typical length between two scattering events? Can we monitor the signature of weak localization? Can we have an idea of the mechanism behind the localization? That's really the game that we want to do with this ultra-cold atom system, not only to have the result, which is nice, but also to try to understand it to go behind. So in fact, there was a very nice idea from Nicolas Cheroret and co-workers, and there is again Dominique Deland in the game, is, as you will show you now, is that we can find a lot of signature in this, if we look now in momentum space. So let me just show you that first, that what we could do is to observe directly one of the process at the heart of Anderson localization, which is weak localization, and namely what we call coherent backscattering. So I'm going very fast because it was introduced yesterday by Dominique, and he has shown you this beautiful picture from the Cassini-Huygens mission, where there is the sun here, there is the sun here, there is the rings, and then the light is reflected, and then you see the peak. So the idea is that if you send light in the medium, and then semi-infinite medium, then it is scattered. And if you look exactly in the backward direction, it can interfere with somehow the counterpart, the time reversal path, which is exactly propagate exactly in the same path in the disorder, but in the reverse way. And these two interfere perfectly constructively because they acquire exactly the same phase if there is time reversal symmetry in the system. So it has been seen in many systems, as I say, Cassini-Huygens mission. It has been nicely seen in optical system. And in fact, we also have done an experiment just for public. It was shown in Palais de la Découverte in Paris 5 years ago. So can we see that this kind of effects with our ultra-cold atoms? So the idea is what we want to do is to prepare somehow these K waves. So to do that, what we do usually in experiment, we prepare a BEC, but we make it very cold so that somehow it has very narrow momentum distribution, which is centered around 0. So the first things that we can do, the atoms usually are paramagnetic. We can give them a kick to accelerate them for a given time and to give them a velocity that can be controlled. So I can control this K0 and give a velocity. Let's say the atoms will go now upward with a well-defined direction. And the second thing, this also was mentioned that, by Martin, is that we can directly image this momentum distribution. And the idea is to use the trick, what we call time of flight experiment. So this is what is shown in this image here. You have to realize that at the beginning, the BEC is quite small here and centered here. After some time, we release everything. We release the trap, and we let the atom evolve. So if they have a velocity, for instance, which just goes upward, after some time, they will displace by a given distance, which is proportional to the velocity if we wait sufficiently long time. And so that that's the time we wait is called the time of flight. And after a while, when we take the image, we can really correlate the intensity here, the distribution of the atom, to the initial velocity before at the time where we switch off the trap. So you can really think of this image as a real measure, direct measure of the momentum distribution of our atoms. Yeah, I don't want to go too much in details here, but you see that the momentum distribution is not 0, but it's very narrow. So to give you an idea, in fact, at the time we reached a temperature which was on the order of 150 picokelvin. So it is even 2 orders of magnitude almost lower than the temperature I gave you before, given by the correlation energy. So that's why somehow when we reach this kind of domain, we are in the domain of ultra-cold atoms, which was somehow the coolest at the time. That was almost one of the coolest atomic cloud ever produced in experiment. So this is the initial wave, which is going like that, and which is going upward, which a well-defined momentum. Then we switch on the disorder. And what we observe, we let the atom, the experimental sequence is going this way. We accelerate the atom upwards. Then we switch on the disorder. The atom will propagate, will evolve in disorder. And then we do the time of flight, and we look how the momentum distribution have evolved. So you have really to think this image is not an image in real space, but it just shows you what's going on in velocity space. So what you see is that the initial peak here has been depleted because the atoms start to be scattered along a ring, and the ring is nothing else than the elastic scattering ring, because the atoms, if the disorder, and was the case here, is not too strong, the typical effect is just to change the direction, but not to change the absolute values. We don't change the velocity, but just this direction. So here we see that we can really monitor here this change of velocity as the atoms are scattered and scattered. So if we wait and if we just look now backward direction, now the velocity, it will correspond to atoms that now come back in the backward direction. So here you see something that already appears, but if you look at even longer time, so you see that the initial peak has almost disappeared, and you clearly see a peak here with an increase of atom number, if you want, exactly in the minus k0 direction. That means exactly in the backward direction. And this peak is nothing else than the coherent backscattering peak. So I can show it to you here in this image, which tell you are roughly the same. So here you have the initial peak, and when you wait, you see that this peak is decreasing, and then you create the ring, and in the backward direction you have this beautiful peak, and you can really observe the formation of the coherent backscattering peak. So we were really happy on this, and in fact we could do many things on this. I will not discuss too much, but to be sure that this is related to phase coherence, we did an experiment which was somehow very similar to an early experiment done in condensed matter physics, which is like Charvian and Charvian experiment, which is try to play with time reversal symmetry, or at least to try to induce specific dephasing between the two paths. And what we have shown is that indeed, if we try to dephase the path, then we can kill the CBS peak. And if we arrange in a situation where the dephasing is applied locally, but exactly at the middle of the trajectory, then the two passes pick up exactly the same phases, and then the CBS signal should be recovered. And this is exactly what we have found, which is called the CBS revival. And that's, for us, that was really now the direct signature that this CBS peak is really due to the interference of these counter-propagating passes in the system. So just to show you, so this momentum space signature allows us really to pinpoint what is the basic mechanism at the heart of localization. And we can somehow do things also which are a bit different, somehow even simpler in some sense, that now we have looked the loop, but the question is, can we measure this mean free path or mean scattering time? And in fact, here now what I have to do is even simpler. I will just look at the decay of the initial peak as it is scattered in the medium. So I think it's not surprising that this initial peak corresponds to the atom that I call the ballistic atom that has not been yet scattered by the disorder medium. And this proportion, as the time evolves, that is propagating the medium, it's clear that we expect it to decay exponentially with a characteristic time, which is the typical time between two scattering events, which is the scattering time. And somehow this configuration is exactly the same that if you send light in a diffusion medium, of course you have diffusing light here, that is atoms that are scattered, which corresponds to the scattering light or scatters atoms, but you have also, you can see the laser, which is the ballistic light, and this ballistic light, it's well known that is decay exponentially with the distance. So somehow it's exactly the same trick that we can measure. So if we monitor the height here, we can see, sorry, here, that's the typical experiment that I showed, that this is the height in log scale, and this is the time, and you see that we can monitor, and it's very impressive because we can see the exponential decay. We can follow it between 2 decades and to have a very precise measure of the scattering time. So this is very important because somehow what I wanted to show you is that we can have access to the microscopic processes when the atom propagate in the disorder, and not only at the macroscopic one, which is somehow the localization length that, of course, we all want to measure. Just to give you an idea of nice things that can be done, in fact, this experiment can be done by varying the initial momentum or the amplitude of the disorder. And what we have done with that, we have probed the crossover from weak to strong disorder regime. If you remember what was said by Dominique, to probe this, the important quantity is the dimensionless number, which is KLS. If KLS is larger than 1, then you expect weak disorder regime. And when it's below than 1, you expect strong disorder. So you see that we could span well across this regime by let's around 5 orders of magnitude. So this is how the experiment look like. So here I plot the scattering time, which is compared to the Born prediction. So when it's blue, it means that the ratio is 1. That means that we have a nice agreement with Born. And when it's red, it means that there is very bad agreement with the Born prediction. And here, so the two axes is when, so the horizontal one is when I increase the momentum. And here is when I play with the disorder strength, but beware, the disorder strength is going downward. So you can clearly see that, in fact, in the right, in the right upper side, you have the weak disorder medium because you have very large velocity, so very high energy and very low disorder. And inversely, so when we move in this direction, the disorder strength is increasing, the energy of the atom is decreasing, and then we enter the very strong disorder regime. And what we could do with that is we could monitor somehow where is the line KELS equal 1. So we could probe quantitatively somehow the relevance of the Josse-Regel-like criterion in our system. And what we could see here in this like speckled pattern is that, of course, it is relevant, this line, because you see it's somehow refer to a line where the ratio between the prediction of Torres and Born is roughly constant, which is nice. But somehow we find important deviation starting from KLS equal already 40. And when we reach 1, there is already 400% difference between Torres, which is measure, and Born prediction. And when we go there, we could even find something like 2 orders of magnitude. So the first take-home message of this, since it's quite somehow digression, is that when we use this laser speckled potential, we found very strong deviation from perturbative prediction as soon that we try to approach this kind of criterion that is close to the Josse-Regel criterion that tell you in the domain where you want to try to see this Anderson transition. So the take-home message for theoreticians, but also for experimentalists, sometimes use perturbative theory to interpret the data. You have to pay very, very attention to this. And this I will come a bit later on this story. And I will see that this story is also strongly related to the problem of spectral function. So here I'm done almost with this. Just a last advertising things, but Nicola will talk a lot, is that you've seen that we can measure LS, we can measure weak localization process, but in fact, the very nice discovery in this momentum space signature, it was found a few years ago, or around 2012, is that there is a new feature that appears in momentum space, which is called the coherent forward scattering peak, which is in fact here. It's like, so at the beginning, you were, this initial peak was there. It has disappeared since very long time. And when you enter the localization regime, a twin peak, which is called this one, the coherent forward scattering peak, this is the CBS peak, appears. And this has been shown that this is a true signature of Anderson localization, that is strong localization. So this has been observed recently. So it was not possible to observe this in our experiment, but it has been observed in Kick, something similar in the Kick-Rotor system. And I'm sure Jean-Claude Garot will talk about that. So that's somehow the general introduction of the domain. And let me now switch more specifically to the problem of the Anderson transition and what's going on in 3D. Okay, try to move the slide. Okay, so as I said, there has been already 3 experiments where we have find evidences of this 3D Anderson localization. There was one in the group of Brian DeMarco in 2011. It was using fermions at the time. One in our group where we produced an expansion in 3D with laser speckle. It was also laser speckle there. And we tried to make evidence of localization, and a new one in Florence. And for all this experiment, really the goal, I said it again, is to try to measure the mobility edge. And okay, that's first goal. And then if you can do it, then try to look at the critical regime. And in fact, there has been first estimation in this work about the position of the mobility edge. So this is one figures from the work of Brian DeMarco, and the one from the group of Giovanni Modugno and Massimo Inguscio in Florence. But as I already said, you will see that there is some problem with this interpretation. And in order to understand what is the problem there, I will concentrate on our experiment, because we are somehow faced to all the experiments are faced to very similar problem if we skip some technical details. So the idea, So the idea to understand what's going on, let's look here at the typical expansion that we could monitor. What we wanted to see nicely is that if we have low disorder strength, then we have diffusion. And then we increase the disorder, and at some certain point, a typical energy that we would call our typical strength of the disorder, then a transition and the wave will be localized. That would have been the dream, but in fact, what was going on is a bit different. At low disorder strength, I won't show the experiment there, you have to trust me, we could see clearly diffusion. There is no problem with that, we could have nice signature. But when we start to increase the disorder strength, after sometimes we end up with this kind of picture, when you see that maybe a first comment is we monitor here the expansion for a very, very long time. So for people which are not used to ultra-cold atom systems, you have to realize that typical time scale maybe are 10 milliseconds, 100 milliseconds start to be rather long. Looking at seconds time scale is very, very long for the typical energy that we have. So first thing is that we found that indeed it's almost nothing happened, but it moves very slowly. And the fact that it moves can be seen at the center. You see that between 0 and 2 seconds, there is a decay here. And if we look closely at the wings, we could show that in fact, they increase a little bit with time. So to make the long story short, we can in fact interpret this kind of picture by saying that there is a part which is localized at the center, which emerges somehow at the center, when the diffusive part is going slowly away with very slow diffusion on the side. Okay, and this was discussed by showing that we have a very nice agreement between our experiment and theoretical prediction made by Laurent Sanchez-Pancia on our system. So the key point is that instead of having only diffusion and only localization and try to pinpoint the mobility edge, when we enter the strong disorder regime, we have the coexistence of the both phases at the same time. The way we interpret our data is that there is a part which is localized and a part which is diffusive. And the way this is happening, in fact, is not so easy, so difficult to understand. The origin is really coming back to this idea on this Josse-Regel criterion, which I already said, I interpret it at the extreme disorder condition. Once again, it means that the wave doesn't have the time to oscillate once before it is scattered again. So for instance, if you look at optical systems, to reach this value, it was extremely difficult. Okay, so it means that when you want to do that in experiments, you prepare a very nice BEC, you try to make it very cool, you make it perfect as you want. But then you have to somehow switch on a disorder which is extremely strong. And doing so, it's impossible, and no experiment has succeeded to find a way yet. At least I will show you what we want to do to turn on this problem. But if you don't find new solution, when you increase the disorder, what you get is that a very large energy spread of the atom that span across the mobility edge. That means that you expect a part of the atom that are high energy and that will start to be diffusive, and a part of low energy that are localized. So this is bad because, for instance, you can forget to look at the critical regime with this kind of system. If you don't solve this problem, it's impossible to look closely what's going on there. However, you can still do something. You can try to estimate where is the position, the mobility edge, if you know two things. First, you can try from experiment to measure the localized fraction. Here, I skip the detail, but this is something that we can do just by looking at our data. We can estimate what is the localized fraction. The energy distribution, this is more tricky because we cannot measure it directly. What we can measure, I said, we can measure directly what is the wave function in wave space or the momentum distribution, but we have no tool, at least easy tool, to measure directly the energy. So here the problem is the perfect determination of the distribution of energy. And as you will see now, that's why a second somehow digression, I want to show you the % of what we call the spectral function for the typical determination of this distribution of energy. And the reason why there is also discrepancies from the numerics on the estimation will rely, I will show you once again, on difficulties to really measure directly, at least the spectral function. They were not, to say differently, they were not precisely measured or understood at the time the experiments were performed. So let me introduce what is the spectral function. So a little bit of digression. So the spectral function is something which is very general in physics. It's just the function that provides the relation between the energy of a particle and its momentum for excitation if you're in the system. So the idea is to try to look this excitation in terms of quasi-particle interpretation. And for instance, the maximum of this spectral function is called, is referred to the dispersion relation. And as an example, I show you that what can be measured for electrons in metal. So here you have the band. So this is the dispersion relation. And the width is referred to, so the energy width for a given K is referred to the quasi-particle lifetime, which is inversely to the typical lifetime of the particle. So this is a very general function, and for in the domain of ultra-cold atom, it is really at the heart of theoretical prediction. Here, I won't go to the mathematical details, but this spectral function is deeply connected to the green function, and this green function was widely introduced yesterday by Dominique. And what I just want to show you now, that in fact, it's quite easy to show that this spectral function is directly related to the typical time, the mean free scattering time that we can measure in the experiment. So indeed, let me consider a simple situation where we have weak disorder and we send an incoming wave to the disorder system. So before the disorder is switched on, the spectral function is something that is very simple if you have a free state. The K momentum is an eigenstate of the system, so you don't have any energy spread, and the spectral function is just a Dirac centered on the kinetic energy related to the K atoms. Okay, then we switch on disorder. What's going on is that we have seen that already. The atoms start to be scattered along different directions, and I've shown you that we can in fact monitor this in momentum space. So intuitively, we can, it's rather simple to understand this as the scattering as a coupling to a continuum. You have the initial K waves, and via the interaction with the disorder potential, you can be scattered to a whole continuum on final state. And then if you simply apply the Fermi-Golden rule, you realize that you will have a finite lifetime with a typical time, which is the lifetime of an initial K wave when it is entering the disorder system, so that it will give the exponential decay that I've seen before. So the exponential decay is on time, but of course, if you have a finite lifetime, it corresponds to a typical energy width, which is nothing else than h bar over the typical time. So this is how to understand naively the link between what I've shown you on the measurement of the mean scattering, the mean free path or mean scattering time, and the link with a simple picture, what we expect for the spectral function. So this is valid in weak disorder, where we can do this coupling, which is somehow very related to the Born approximation. When the disorder is going strong, this is another story to really determine the real shape of this. So here, if I have time, so it's really depend on the end of the talk, I will show you how they look like. But if I have no time to go to there, then I really suggest you to look at the poster of Pierre Pelletier. The key point is that at the time the experiments were done before, it was not clear how the spectral function looked like, and sometimes this kind of naive interpretation was used. So let me come back about our problem. So as I said, this spectral function will help us to measure the energy distribution. In fact, it's quite easy to realize, since this is the function that relates what is the momentum distribution, what is the energy, sorry, for a specific momentum distribution. So what we can do in experiment, we can measure the momentum distribution. I've shown you that we can do that by the time of flight experiment. And then if we know this, but this is something that we have, which is not direct, that we have to compute or to estimate by any methods that you have at hand, then you can estimate what is the energy distribution, but it's important to realize that it's not a direct measure. This is all how the experiments were interpreted. Then I think I insist quite a lot of that is that if you don't have a precise and reliable determination of the spectral function, then it will be difficult to interpret the data. Okay, with that in mind, I will show you now how the results look like.
So you have 5 minutes left.
Perfect. I think the idea is I want to finish explaining that, and then I will be very rapid on the end. It's less important. I think the main message I wanted to tell are there. So the very nice thing is that now, since 2017, there was a new work by Michael Pasek, which was a postdoc of Dominique Deland and Giuliano Orso, where they could estimate where is the position of the mobility edge. This is very difficult numerics, but now they can try to do it. So here, this is what I'm showing you. So in a vertical axis is the position of the mobility edge, but it is referred to the mean value, 0 here. So if I come back to this graph, here you have the mean value of the disorder potential, so it is referred to 0 in this graph. So if it's negative, that means here the position, which is here shown by the numerics, you see that it's below the average value of the disorder. And it evolved when we change the disorder strength. And this is normalized here to the important quantity I've introduced you before, which is the correlation energy. And the very nice thing is that you can really, if you measure for any experiment, what is your sigma, you can put all the experiment on a single line. You can renormalize all the experiment, which was indeed showed by Dominique and co-workers. So now I can compare on this graph the estimation for all the 3 experiments that I've shown you before. So here are the results. So you see here, first, the one that we've done in a long time ago, so in 2012 in Palaiso, I have to say that it was rather indirect. That's why it is a straight line. This is just an estimate of the mobility edge using all the data that was published at the time. But at the time, we didn't want to estimate too much the mobility edge because we knew that it was rather indirect. But the main message here is that if we plot our estimation to the numerics, you see that it is, in principle, very good, at least seems reasonable. The only point here, it seems that at long time here, at large energy, it starts to deviate. But the key point is that this is just an extrapolation of what we can measure in this regime. And this regime here, I won't enter too much there, but it's called the quantum disorder regime. So it seems very small in this graph, but we could, of course, pan here. And for us, it is one of the most interesting ones because it's called the quantum disorder regime, where you have really somehow the genuine Anderson localization. When you go to very strong disorder, then you are more and more classical, and you expect this mobility edge to reach at some point what we call the classical perturbation threshold. Okay, so this is our experiment, so it's not too bad, but I insist it is an indirect estimate. I won't claim that we had a measure, and clearly we want to do better than that. Here is the experiment of Florence. I won't enter the detail, but in many sense, it is a very nice improvement of what we could do, because they could measure a bit more directly the spectral function, but okay, at least no, they estimate the spectral function by numerics, but they really measure the momentum distribution. I mean, they try to do fancy things to have a more direct estimate, and you see that it's not so bad, but it's still far from really what we expect it to be. Okay, so my point is not to say that these experiments are bad. They are very nice experiments in Florence, but just to say that in fact it's very difficult to have everything under control, to have clear estimates on the mobility edge. And you see that here it misses one curve, which is the one of Brian DeMarco. In fact, the problem of Brian DeMarco is that you could see it, but then you have to change a lot of the scale. Okay. It was somehow done at much more energy in a very different regime. And also you can clearly see here that the estimate that they've done is clearly off. And I don't want to enter too much the debate here, but there is a lot of problem clearly in this work. Maybe one of them, if you realize, to explain what we have done before, I told you that to try to see this localization, we went up to 6 seconds to be able to differentiate between localization and slow diffusion. In this experiment, they went only for 15 milliseconds. So that means the first problem is that they can barely not see if this is slow diffusion of localization. So this is a first problem. And the second problem, it's more fundamental. It's related to the way they use the spectral function to estimate their data. And in that case, they use something which is a very, very bad approximation. They use a delta function as if they were free particles. And as I've told you before, when you enter the strong scattering regime, the extreme disorder, clearly the spectral functions are very, very different from that. And these two effects makes that the results are clearly far from the prediction of the mobility edge. So I'm almost stopped with that. So it's like the preliminary conclusion, but it's good also for full conclusion, is that there has been landmark experiment done for the 3D Anderson localization. But if we want to go to do something better, then we have to have a much better control over the energy distribution. First idea will be, can we measure this? And this is really related to how we can really have a precise knowledge of the spectral function. So if we want to learn more on that, I suggest you to listen the poster of Pierre. More important, here is somehow, okay, we have large things, so it's not so good. We can try to do something if we measure it. It's good, but it's still not really satisfactory. The really good things will be to be able to control it, to have something and then to have these broad things, to have something narrow that we can control, and we can span across the mobility edge and do something like that. So that means to try to find a way to have selective population of energy states. So if I'm mentioning that, is that indeed it's what we try to do at the moment. So just give you a rough idea of what we are doing, and then I conclude. So this is the last part, which is the spectroscopic scheme with state-dependent disorder. So the idea, what we want to do is now we change. We have two states, and we will do a spin transfer to select precise energy level in the disorder, and that we can scan. Okay, so this is the scheme that I've shown you here in the sketch version there. We have the BEC, we transfer it to a well-defined energy, and we scan the energy here at will. And then we hope to try to probe the mobility edge like that. So this is a new scheme, which is called the spectroscopic scheme. And I skip it like that. But clearly here, it's just for people to realize how it is doing. It's just that the final energy is the one plus the one of the RF frequency. So by tuning the RF frequency, we can tune the energy. And the energy width is simply related to the inverse of time of coupling. And we have shown preliminary result because we could measure the spectral function. And we found something as low at 10 Hertz. And this is already 2 orders of magnitude better than what I've shown you in the experiment before. So we have really great hopes to do something with this. I skipped the realization and the fact that with this, we can measure the spectral function. But at the end, with this system, the first thing that we have done is to measure the spectral function. We found it that they are quite weird. Once again, it's very related to what I've told you before. It's like the take-home message BIS, that beware when using perturbative approaches to address the Anderson transition, which is rather obvious, but it's good to measure it. And I finish with that, just because we are doing here within the Simon's collaboration, just to telling you that, in fact, one of the subjects is to be able to make nice prediction of the spectral function. And we have great hopes to be able to do it with the landscapes theory. And this is the work of the PhD thesis of Pierre Pelletier at the moment. And it will show you a preliminary result. But just to showing you the real one is something like that. There is a weird peak somewhere, which is the peculiar feature. And prediction are really promising at the moment, but this is ongoing work. Okay, I'm sorry to be a bit long. I hope it was clear enough, and thank you for your attention. And I just, of course, mention all the PhD students and postdocs that have worked on this.
Okay.
Me and Alain.
Okay, thank you, Vincent. We have time for very quick questions, and I think that we will have more time to discuss in the poster session or in the after breaks. So if there is one quick question here, seems to.
It was too clear.
Yeah. Okay, I have a question from Donald White.
Okay.
Please, Donald, unmute your.
Okay.
Okay.
Thank you very much for the nice talk, Vincent. I was just wondering if there's perhaps a different way to do the mobility edge measurement in this kind of a direct analogy to the scaling theory, where you measure d log G, d log L. If you were to do a kind of a transmission experiment, could you do this? Could you do a measurement like that?
I think doing a transmission experiment, okay, Donald, we haven't met together, but you're working in the 2D experiment with Martin, right?
Yes, that's right.
So I didn't mention it, but of course, all the experiment that shown is based on expansion, but there is the way to do the transmission. And this is, I wanted to mention it and I forgot, so sorry for that.
Okay.
And this is what you are doing, and it was very along the line of the work of Jean-Philippe. I think in 3D, it's almost impossible to do that because you have to put something and then to go everywhere. So that will be able to measure on a sphere in 3D. So that's very, very, very difficult, whether it is quite reasonable and ideal to do that in 2D and also in 1D. So I believe doing as the scaling, of course, that will be a dream to try to do this transport experiment, because many ideas for understanding localization were done in this system on transmission, because that is something that you can do in condensed matter. This is something that you can do in optics. So there is a lot of theory framework for that. But it is not something I believe it's feasible in 3D. At least I don't know how to do it. But of course, we think at some point to try to do it, but I believe it's too complicated. But thanks for the question. Of course, it will be nice to do it.
Exactly.